before we can start talking about gas laws, we need to talk about what are measured and how each of these measured quantities are affected by each other. So the four quantities that you can easily measure for gases: pressure, volume, temperature, and the number of moles, or the amount. So pressure P, volume V, temperature T. It's important that it's in Kelvin. It has to be in Kelvin for these calculations to turn out right. And then moles is abbreviated N. So whenever you determine a gas law or derive the gas laws, it's important to note that you're looking how two of the variables or properties are related. You have to hold the other two properties, the other two variables, constant. Okay, so put that into action. If you remember one equation from chapter 9, or gas law equation, it's this one. PV is equal to NRT. That relates pressure, volume, the amount of moles of a gas, and the temperature of a gas to each other. And from it you can derive the simpler gas laws. And so how do you do that? What these numbers mean, these subscripts mean. So 1 represent, condition 1. 2 represents condition 2. What that means is that you can look at changes. So if you start at one pressure and move to another pressure, or one volume and move to another one, those are represented by those 1 and 2 subscripts. So if I want to look at how pressure and volume are related, that means that if you hold N and T constant, that would mean that N1 is equal to N2. And T1 is equal to T2. If N and T are constant, that means they are not changing. That would mean that the condition for the amount of gas that you would start with would be the same as what you would finish with. Same for temperature. So since N1 is equal to N2, that means that they cancel in this equation above. So if N1 is equal to N2, that means it's the same number. Any number divided by itself is equal to 1. The gas constant we'll talk about a little bit later, but it is a constant. R is equal to R. Those cancel. So we get P1, V1 for P2, V2 is equal to 1. And to rearrange that, we get our first gas law, simple gas law, P1, V1 P2, V2. This is Boyle's law. And what that means is that pressure and volume are inversely proportional. Okay, so that means pressure is proportional to 1 over volume. Okay, as the pressure goes up, the volume goes down, and vice versa. So you could do the same type of process to derive Charles' law, which relates volume and temperature, and Avogadro's law, which relates volume and the amount of gas. So the ideal gas equation, PV equals nRT. R is the ideal gas constant, and what's on this picture, on this slide, is showing what that constant is and where it comes from. So it's a measured value, and standard conditions, okay, what that means is when you're doing experiments with gases and you want to standardize those conditions, STP, standard temperature and pressure, is defined to be 1 atmosphere of pressure and 273 Kelvin, 0 degrees Celsius. So cold, but 273 Kelvin. Under these conditions, it was found that a mole of any ideal gas occupies a volume of 22.4 liters. Whether it was a mole of helium or nitrogen gas, oxygen gas, that 1 mole of that would occupy this volume. Okay, so if you've got 1 atmosphere of pressure, okay, standard pressure, that experimental value of 22.4, 414 is the full value, but for calculations later we'll use 22.4, 1 mole of gas, then 273.15 Kelvin. That's the full value. Calculations later we'll use 273. That is where the ideal gas constant comes from. So a typical gas law problem. The volume of a gas is 2 liters at 5 atmospheres of pressure. What is the final pressure if the volume is increased to 5 liters at constant T? If we write PV nRT yes, condition 1, condition 2, the volume of the gas is 2 liters and the pressure is 0.5 atmospheres. So we've got V1 is 2 liters, P1 0.50 atmosphere. What's the final pressure? That's the question. If the volume is increased to 5 liters. Well, so the equation we need is the one that relates volume and pressure. And we're told that the temperature is constant, the gas constant is constant, and the volume of the gas, what's the final pressure of that gas? If the gas is contained, that means that the amount of the gas is not changing. From earlier, we see that P1, V1 is P2, V2. So Boyle's law. So now it's doing a little algebra. P2 is P1 V1 over V2. Just divide both sides by V2. So 0.50 atmosphere times 2 liters divided by 5 liters liters cancel, we're left in pressure. And that will be 0.20 atmosphere. And that should make sense. So if pressure and volume are inversely proportional, which they are, that means if volume goes up, went from 2 to 5, that means pressure has to go down. And 0.2 atmospheres is less than 0.5 atmosphere. Another simple gas law problem. What volume will a sample of gas occupy at 400 degrees Celsius if it occupies 420 milliliters at 100 degrees Celsius? The pressure is constant and the sample gas amount, the number of moles, isn't changing. So we have V1 is 420 milliliters. T1 is 100 degrees Celsius, but Kelvin, that's 373 Kelvin. Remember, you have to add 273 to convert Celsius to Kelvin. V2, what volume will a sample of gas occupy? That's the question. And T2 is 400 degrees Celsius. Kelvin, that's 673 Kelvin. So this question is asking about the relationship between volume and temperature. Equation, what equation do we need? The amount of the gas is being held constant. The pressure is held constant. And the ideal gas constant is a constant. So all of those variables are being held constant. They cancel. They're not changing. So we have V1, V2, T1, T2. Now to rearrange that, this is Charles' law, volume and temperature. Do a little algebra. But you see that V1 over T1 is equal to V2 over T2. If you do a little algebra. Here we solve. The question is asking for V2. That means V2 is equal to V1 T2 over T1. That's the equation that's needed. plug and chug, 420 milliliters, times 673 Kelvin, divided by 373 Kelvin. We're left in a volume in milliliters. If I do my math correctly, I get 758 milliliters. In Charles' law, if we look to see if that makes sense, we've got volume and temperature being directly proportional, meaning that as volume goes up, temperature goes up, and vice versa. If we look here, the temperature increased, the volume increased. So the answer does make sense. It should be larger than the initial volume.